major issue on the internet, and it's a craft, not a science. We survive because the people who are configuring BGP know their job. What would you do to make sure that an AS actually follows the path that's being advertised? Because you can imagine, using digital signatures or cryptography to make sure that a prefix, you cannot hijack a prefix. What about making sure that a packet actually follows the path?
You send a packet onto a tracer and see if it follows the road that the AS advertised.
Right, so you could send a packet. You can't quite trace the path that packet took. You could use tools like traceroute to see what paths the packet follows, but it's actually a really hard problem and an unsolved problem to make sure that a packet followed the path that you thought it was going to follow. I would say that's a pretty open problem. So you could put a path that you want the packet to follow and hope, but if you have a malicious AS that's not following it, the fact that you said what path you want followed is... so every hop along the way would have to do that. Yes, that would work. Any other thoughts or concerns around BGP security? Okay, so the short answer is that BGP security is a bit of a mess, and that's why people are very, very careful in who and how their BGP policies and advertisements are configured. Performance, thoughts on performance. So I have a hint here in saying that they're performance non-issues, but can you see a concern around performance with BGP? And so performance here tends to be short paths. Yeah? Non-optimal. I would go beyond what you said and say that in general, policy-based route selection is not about picking short paths, right? It's about enforcing policy. So the path you picked based on policy need not be the shortest path. So I said this was a non-issue because this is not by accident. This is by design. Operators are choosing to prioritize policy over path. The other aspect, though, is that your AS path length can be misleading. So if I say I have a one-hop AS path length, there's nothing in BGP or no easy way that allows me to distinguish between that was one AS hop that involved 2 routers, both in California, versus one AS hop that involved 20 routers spread across the globe. Right? That detail is actually hidden because we are abstracting all that into an AS path. Again, this is by design. ISPs and ASs don't want to reveal their internal topology, but it does have this implication for performance. Prone to misconfiguration, someone brought this up. We have many attributes. The configuration is often manual and ad hoc. Again, configuring BGP, there's a relatively small number of people who are trusted at large operators to actually configure BGP. Anytime there's a configuration change, it's done very carefully, it's tested, it's vetted, and we still have major issues. So BGP misconfiguration is probably the root cause of outages on the internet. And if you Google some of the famous BGP outages, it's quite entertaining. So the examples like Pakistan wanted to censor YouTube, and so they wanted to put in configuration that would filter out routes advertising YouTube. And they got it wrong, and so by mistake they started advertising YouTube to the rest of the internet. And so all YouTube traffic went into Pakistan, exactly the opposite effect. Russia, I think, had a similar thing with Twitter recently. Somebody did prefix hijacking to hijack all the traffic going to one of these crypto companies and managed to actually steal millions of dollars doing that. So BGP hijacks and some of them are malicious. A very large number of them are actually just unfortunate misconfigurations. Okay. And finally, reachability and convergence. I touched on this last time. If you follow GAU-Rexford, good things happen. If you don't follow GAU-Rexford, all bets are off. There's no guarantee even that all destinations would be reachable or that you'd have convergence. And in section, you're going to see this very fun example of how, if you don't follow GAU-Rexford, you could have continuous oscillations in which path you're selecting. So routing actually never converges. Okay, so with that, any questions? Okay, let's take a 1-minute break. We are kind of done with BGP at this point. So any last questions on BGP? Yeah. Yeah. All right, let's keep going. So, rest of today's lecture, I just want to take stock of where we are in the overall syllabus in some sense. We started with this overview of how the internet works, top down, bottom up, and then we jumped straight into L3, or the network layer, which is arguably the most important layer on the internet. And we spent many weeks doing routing. We've done intra-domain, inter-domain, we've done addressing. So at this point, addressing and routing, which I would say is the control plane for the network layer. I hope you got that we're fairly complete on that front. Where we're going to do this week is go back to the L3 or the network layer data plane. Okay? So today's lecture, we're going to talk about what the IP data packets actually look like, and specifically what the IP header looks like. And then next lecture, we have a guest lecturer from Google who's going to teach us about IP routers, how they're built, how they function. And we're kind of really lucky to have him because he is the person that represents Google to all router vendors, so he really knows what he's talking about. And he also defined some of the main router management and router configuration protocols that are in use everywhere today. So OpenConfig, if you Google it, you will find Rob's name. So today let's talk about designing the IP header. Okay? And designing the IP header, if you remember going back to one of our earliest lectures, we said we have packets, they have headers and payloads. We tend to not worry so much about the payload because, especially at the network layer, routers are not looking at the payload. But the header is where all the action is, and so that's what we're going to be focused on. So we're going to talk about the syntax, like what fields and how many bits for the IP header. I know that sounds very boring. We'll try to make it not so boring. But more importantly, the semantics. Why do we have those fields? What do we use them for, and so on. Just a quick recap to get your head back in the right place. Remember, we had talked about layering. So keep in mind where L3 and L3 headers fit between L4 and L2, and how we talked about encapsulating packets in headers and then removing headers when you reach the destination. Okay? Also remember, we had this complicated end-to-end protocol diagram. The thing to remember here is the fact that the IP header or IP portion of the packet is relevant both at routers and at end hosts. It really is the end-to-end interface or language. Okay? Any questions or reminders on the IP header in terms of its role at that high level? No. Okay. So designing the IP header, when you think about designing the IP header, the way to think about it really is not so differently from how you would think about designing an interface. Right? Anytime you have to build a system, you kind of start by thinking about the interface. So think of the IP header as the interface between the source and the destination end system, but also the interface between the source and the network routers. Right? So it would not be an exaggeration to say that the IP header is the interface to the internet. So it's kind of a cool interface to design. So when you design it, anytime we talk about designing something, first thing you should ask yourself is, what's the goal? Right? So in this context, what task am I trying to accomplish? And this, again, should be no different from when you design an interface for any piece of code you write. Right? Your module has a certain function. Your interface has to pass the parameters and the information so that that module can do its job. It's going to be exactly the same with IP. We're going to say what tasks are we trying to accomplish, and then what information do we need in order to accomplish those tasks. And then your IP header is just simply how we capture that information. Okay. So with that, what are these tasks? And remember, IP headers are relevant at routers and they're relevant at the destination host. Right? This is the sender communicating both with routers and the destinations. So I'm going to give you one example. The first thing you should do when you receive a packet, you have to be able to parse it. Right? You have to know what kind of packet is this. Is this an IP packet? What fields are there? So parsing the header and the packet is job number one. We're going to have to do this at routers and at the destination. What else? What was the job of IP? How to forward it? Absolutely. That was the primary role of IP, right? So you're going to need information in the header that allows the router to forward the packet. What else do we have to do? So what's the normal path for a packet, right? So we forwarded it, what happens when it reaches the destination? Get at the payload. Yeah, I'm going to find that. So it kind of tell the destination what to do with the packet, right? So I need to be able to parse the packet at both routers and destinations. I need to be able to forward the packet on to its destination. This is a task that the routers have to do. When the packet reaches the destination end host, the destination has to know what to do with it, because remember, the packet is not really, it's not headed to the destination, it's headed to some application at the destination. So there's something in the packet header that has to allow the destination to figure out how the packet has to be sent next on its journey towards the application. We'll get to that in a minute. And then, for most practical purposes, we're going to need a response going back to the source. And so again, the destination host has to know how to send the packet back to the source. This is a task for routers as well, and we'll get to why that is in a minute. So this is kind of all you would need to do in a well-functioning, pretty bare bones network. Anything else you can think of? Yeah. Yeah. Okay, so I'm going to broadly call that deal with problems along the way, and we'll get into what potential problems you could run into. And also then the ability to specify some kind of special or more advanced processing that we haven't quite gotten into so far, so we'll get into that as well. So these are kind of the tasks, the consolidated list of tasks. This is all the tasks that you need to capture in the IP header, that your IP header has to have all the information needed to accomplish this set of tasks. It's not such a long list, actually. Okay. So let's go through these a little quickly. They're fairly intuitive, I think. To parse a packet, what information would I need in order to know how to parse this packet? Yeah. Size of the payload. Anything else? Size of the header. Yeah. IP version number. Okay, great. Oops. You got all of them. So first, version number for IP. Why is this so important that I have a version number? Yeah, because if you didn't have a version number, you would be stuck with the same header forever, for eternity. Right? So when you had IPv4 and you wanted to go to IPv6, if you needed a different format for the header and you didn't have a version number, good luck. Right? You wouldn't have been able to implement it. So a version number, just like you have versions for API, is critical. Also, where does the header end? This is because, as we'll get to in a minute, the IP header is not a fixed size. So you have to know how many bytes form the header. And then remember we said IP packets are not all the same size. So you also have to know where the packet ends. Okay. In order to deliver the packet to the final destination, what information do you need in the header? We've had this, assume this throughout. Yeah. Oh, you jumped, but yes. To get to the destination, you need the destination address.